In this video, we'll be using the alternating series test to determine whether a series converges or diverges. An alternating series is a series whose terms alternate signs. If the series is of the form the sum from n equals 1 to infinity of negative 1 to the n a sub n, when n equals 1, we get negative a sub 1. When n equals 2, we get positive a sub 2. When n equals 3, we get negative a sub 3, and so on. So that our odd terms are negative and our even terms are positive. If the series is of the form the sum from n equals 1 to infinity of negative 1 to the n plus 1 times a sub n, then the even terms are negative. In this case, when n equals 1, we get a sub 1. When n equals 2, we get minus a sub 2. Then plus a sub 3, and so on. The alternating series test tells us that when we have an alternating series of the form negative 1 to the n times a sub n, or negative 1 to the n plus 1 times a sub n, it will converge if the following two statements are true. First, the limit of the nth term must equal 0. And second, the n plus first term must be less than or equal to the nth term. In other words, we have a non-increasing series, and that must be true for all terms greater than or equal to some fixed starting point that we're calling here capital N. Proof of the alternating series test. We want to assume that a sub n is positive, that the limit of the nth term as we approach infinity is 0, and that we have a non-increasing series for all n starting at some fixed point, capital N. We need to show that the alternating series, negative 1 to the n plus 1, a sub n, converges. Let's start by looking at the partial sums. The nth partial sum is given by s sub n, and it means the sum of the first n terms. If n is odd, then the nth partial sum is a1 minus a2 plus a3 minus a4, and so on until we get to the last term, a sub n. And if n is odd, then that last term has a positive value. We can represent the sequence of the odd partial sums, in other words, s sub 1, s sub 3, s sub 5, s sub 7, and so on, with the sequence s sub 2n minus 1. 2n minus 1 will give us all of the positive odd numbers. If n is even, then our partial sums end with a negative value. And we can look at the even partial sums by s sub 2n. S sub 2n will give us s sub 2, s sub 4, s sub 6, and so on. So we get all of the even partial sums. If we look at the even partial sums, we're always adding pairs of terms. And because this is a non-increasing series, we're always, the magnitude of the value that comes next is always smaller than or equal to. So the a sub 1 minus a sub 2 is a positive number. A sub 3 minus a sub 4 is also a positive number. A sub 5 minus a sub 6 is a positive number, and those positive numbers are getting smaller and smaller and smaller. So our sequence of partial sums contains strictly non-negative terms, therefore it's monotonic and bounded below by 0. If we rearrange our terms, and all I'm really doing is redistributing my parentheses here, so I'm putting the parentheses here and making that a negative sign instead, then I get a different representation of my even partial sums. And here we can see that this is bounded above by the first term, because a sub 2 minus a sub 3 is positive, a4 minus a5 is positive, and so on. So I keep subtracting a positive amount, and the amount I'm subtracting is getting smaller and smaller and smaller. So the largest possible value of this sum is just the first term, a sub 1. Since the sequence of even partial sums is both monotonic and bounded, it converges to some value L. And we can also represent the even partial sums as the odd partial sums minus a sub 2n. S sub 2n minus 1 means we're adding up all of those terms until we get to the a sub 2n minus first term. So the very next term after that, we would just add 1 to this subscript here, and 2n minus 1 plus 1 gives us a sub 2n. And in this series, all of the even terms are negative, so that's why it's minus a sub 2n. Now, one of our assumptions in the beginning was that the limit of the nth term goes to 0. And if the limit of the nth term goes to 0, then the limit of a sub 2n must also go to 0. Because a sub 2n just means we're farther along in the series. So now we have the limit of the even partial sums equal to the limit of the odd partial sums minus the limit of a sub 2n as n goes to infinity. And all I did there was take the limit of this term and set that equal to the limit of this term minus the limit of this term. So that came directly from this equation right here. And we know that this is approaching 0. So the limit of the even partial sums is just equal to the limit of the odd partial sums. And those are both then equal to L. Since the limit of the even partial sums is equal to L, then the limit of the odd partial sums must also be equal to L, since the even and odd partial sums are equal to each other. Since both the odd partial sums and the even partial sums converge to the same limit L, the sequence of partial sums must also converge to L. And if the sequence of partial sums converges, then the corresponding series also converges. Let's look at how we can apply the alternating series test in the following examples. Number 1 is an alternating series. It's in the form -1 to the n plus 1 times a sub n. So here we have a sub n equals 1 over n. To use the alternating series test, first we check that the limit as n approaches infinity of a sub n, which in this case is 1 over n, goes to 0. And the limit of 1 over n as n approaches infinity is 0. So we've satisfied the first condition. And the second thing we have to check is a sub n plus 1 less than or equal to a sub n. A sub n plus 1 would be 1 over n plus 1. A sub n is 1 over n. Comparing these two fractions, the one on the left is always going to have a larger denominator, therefore it'll have a smaller overall value. So the n plus first term is always less than the nth term, and that is true for all n greater than or equal to 1. Therefore, our series n equals 1 to infinity, -1 to the n plus 1, 1 over n, converges by the alternating series test. You may want to pause the video and try examples 2 and 3 on your own. For number 2, let's start by rewriting the series. I'm going to factor out a -1 to the n minus 1, so it's going to be n over -1 to the n minus 1 times 2 to the n minus 1. And that's the same as -1 to the n minus 1 times n over 2 to the n times 2 to the -1, which is the same as -1 to the n minus 1 times 2n over 2 to the n. This is an alternating series. My a sub n is 2n divided by 2 to the n. To use the alternating series test, first we take the limit as n approaches infinity of our a sub n, which is 2n over 2 to the power n, that limit is 0. Exponentials grow faster than polynomials, so the limit is 0. Or we could also use L'Hopital's rule to show that. So we've satisfied the first check, and then we check to see is a sub n plus 1, so 2 times n plus 1 over 2 to the power n plus 1, is that less than or equal to 2n over 2 to the power n. Now if I multiply the numerator and denominator by 2 over here, then in the denominator I have 2 to the power n plus 1, which matches the denominator of the fraction on the left. So now I can, since the denominators are the same, I can just compare the numerators. Is 2 times the quantity n plus 1, which is 2n plus 2, is that less than or equal to 2 times 2n, which is 4n? 2n plus 2 is less than or equal to 4n for all n greater than or equal to 1. So we've satisfied the second condition for the alternating series test. Therefore, this series does converge by the alternating series test. Number 3, we have an alternating series with a sub n equal to n plus 1 over n. To use the alternating series test, first we're going to take the limit as n approaches infinity of n plus 1 over n. That limit is equal to 1, which is not 0, so we have failed to satisfy the first condition of convergence. Therefore, the series diverges. Next, let's look at the alternating series remainder theorem. Let the sum from n equals 1 to infinity of negative 1 to the n plus 1 a sub n be a convergent alternating series such that a sub n plus 1 is less than or equal to a sub n for all n starting at a fixed value, capital N. This means that our terms are either strictly decreasing or equal to the previous term, so we have a non-increasing series. R sub n represents the remainder when we use S sub n to estimate S. So we have R sub n equals S minus S sub n. S is the infinite sum, S sub n is the nth partial sum we get by adding just the first n terms. So this series represents our infinite sum S. We're going from 1 to infinity, negative 1 to the n plus 1 a sub n. Minus, this is our nth partial sum. We're only summing the first n terms. So the difference between these two will give us our remainder, R sub n. If we take away the sum of the first n terms, what we have left is a sum that starts at the n plus first term. And now, since our sum starts with big N plus 1, that's what we would substitute in first, giving us negative 1 to the big N plus 2, a sub n plus 1. And then we increase our index by 1, so then we would plug in big N plus 2 and get this next term, negative 1 to the big N plus 3, a sub n plus 2. Now I take the absolute value of both sides, and on the right-hand side we're going to factor out negative 1 to the n plus 2. When I factor out negative 1 to the n plus 2 from this first term, I'm just left with a sub n plus 1. When I factor out negative 1 to the n plus 2 from the next term, I'm just left with negative 1 to the power 1, giving me a negative for my second term, and it will continue to alternate. Because I'm taking the absolute value of negative 1 to the n plus 2 is just going to be a positive 1, so that drops out and leaves me with just a sub n plus 1 minus a sub n plus 2 plus a sub n plus 3, etc. The overall value of what I have left here is positive because each successive term is smaller than the previous term. And if I redistribute my parentheses by factoring a negative out of these two terms and factoring a negative out of the next two terms and so on, then my series looks like this. this has a positive value because a sub n plus 3 is smaller than a sub n plus 2. And so each successive pair of numbers is going to have a positive difference. I'm continuing to subtract positive numbers that are getting smaller and smaller and smaller. And so this sum is going to be bounded above by this first term. And so I have the absolute value of my remainder less than or equal to a sub n plus 1. This means the remainder, when we're taking the nth partial sum, will be no greater than the first neglected term. To summarize, the alternating series remainder theorem tells us if we have an alternating series that is convergent, where a sub n plus 1 is less than or equal to a sub n for all n greater than or equal to big N, then the absolute value of the remainder will be less than or equal to a sub n plus 1. Let's try using the alternating series remainder theorem to approximate the sum of this series by its first 6 terms. The conditions that must be met: first, it has to be a convergent alternating series, so we're going to apply the alternating series test. We take the limit of a sub n, in this case, which is 1 over n squared. Take that limit as n goes to infinity, and that is 0. So we satisfy the first condition of the alternating series test. Then we want to see if the n plus first term is less than or equal to the nth term. Comparing these two fractions, the fraction on the left will always have a larger denominator, therefore it'll always have a smaller overall value. Therefore the series converges. And so we may apply the alternating series remainder theorem in this case. We're going to use the first 6 terms to approximate the series. To find the first term, we let n equal 1. So we have negative 1 to the power 2 over 1 squared. To get the next term, we have negative 1 to the power 3 over 2 squared. The next term, when n is 3, we have negative 1 to the power 4 over 3 squared, and so on. Once you start to see the pattern, you can fill in the next few terms pretty quickly. So we want to use the first 6 terms and find that sum, which is approximately 0.811. Now the remainder for summing the first 6 terms is going to be less than or equal to the value of the 7th term. And the 7th term would be 1 over 7 squared, which is approximately 0.020. So our sum falls within the range of 0.811 plus or minus 0.020, which means our actual sum falls within the interval 0.791 to 0.831. For our last example, we're going to find the sum of the series correct to 3 decimal places. This is an alternating series. Our a sub n is 1 over n factorial. So first let's check to make sure this is a convergent alternating series. So we find the limit as n approaches infinity of 1 over n factorial, and that is 0. Next we check to make sure that 1 over n plus 1 factorial is less than or equal to 1 over n factorial. And n plus 1 factorial is larger than n factorial. A larger denominator means a smaller overall value. Therefore, our series converges by the alternating series test. And now we know that we're looking for the remainder. Correct to 3 decimal places is going to mean less than 0.001. And r sub n is less than or equal to a sub n plus 1. And we want that to be less than 0.001. a sub n plus 1 is 1 over n plus 1 factorial. We want to find where is that less than or equal to 0.001, or where is n plus 1 factorial greater than or equal to 1000. 6 factorial equals 720, so that is not greater than or equal to 1000. 7 factorial is 5040, which is greater than 1000. So n plus 1 is 7, or at n equals 6, which means s sub 6 will approximate the sum correct to 3 decimal places, and s sub 6 is just the sum of the first 6 terms. When n is 1, we get negative 1 over 1 factorial. At n equals 2, we get plus 1 over 2 factorial, and then minus 1 over 3 factorial, plus 1 over 4 factorial, minus 1 over 5 factorial, plus 1 over 6 factorial, which is approximately negative 0.632. In this video, we've seen how we can use the alternating series test to determine whether alternating series converge or diverge, and we've also seen how we can use the alternating series remainder theorem to measure the size of our error when we're using a partial sum to estimate an infinite sum of an alternating series.